One of the areas of this course that I certainly find a little bit tricky to teach is the further symmetry properties. The Pythagorean identity, not so much, because it's based on something that you guys have been doing since year 9, which is Pythagoras' theorem. Okay, so if you look at this particular right-angled triangle from the unit circle, what we note here is that we form this right-angled triangle, and we know that for any right-angled triangle, Pythagoras' theorem holds, which is the square of the longest side is equal to the sum of the squares of the two shorter sides. Now, the two shorter sides at this stage happen to be cosine and sine. So if we square those sides and add them, it'll be equal to the square of this side here, which is, well, 1 squared is 1. Now, one thing to note about the Pythagorean identity and notation is that if we're doing cosine theta all squared, it's actually more commonly written like this. And I don't love this notation because it looks like we're going to square cosine for whatever reason and multiply the result by theta or something like that. But actually this is exactly the same as cosine theta all squared. Okay, and that's the way we choose to, or a lot of mathematicians choose to write that. You can write it like this as well. What you're not allowed to do is write it like this, cosine theta all squared, okay? Or cosine theta in brackets squared, because that could be confusing, because do I square theta or do I square the lot? I'm not too sure which one. So you've got to be clear on what you're trying to do, and you're allowed to either use that or that notation. I'll be using this predominantly. The Pythagorean identity is not on the formula sheet, okay, so you'll need to remember that, but it's based on Pythagoras' theorem, so I hope you'll be fine with that one. Cambridge uses this identity a couple of times in its simplifiers, so I just wanted to point this one out to you, that if you ever get to the point where you've got cosine theta all squared, take away sine theta all squared, you can actually replace it with this, which is 2 lots of cosine theta all squared, take 1. Now, how is that the case? Well, I'm not really going to show it, so I shouldn't say that this is a show, but we're going to say indicate that this is the case. All right, so it's based on the Pythagorean identity, so I'm going to write that out first of all. So cosine theta all squared plus sine theta all squared equals 1. And what I'm going to do is get it to this point here. I need to get rid of this sine. So I'm going to make sine theta all squared the subject. Now what I'm going to do is, for this definition of sine theta all squared, I'm going to slam in what it's also equal to. So I've got cosine theta, take away 1 brackets cosine theta all squared. Now let's see what that equals once I expand those brackets. And I've got 2 lots of cosine theta all squared. Take 1. And there's my kind of the way that I can say that that's the case, because I know that this is the case. So I manipulate this, shove it in when I've made the correct thing the subject, and I get that. So whenever you see that in your working out, you can replace it with this. And from memory, I can't really remember the questions from Cambridge, but I remember I put this in the notes to kind of prepare you for that. But whenever you see this, you can make this move on it to further engage in the problem. All right, similarly, it works on this one here. So if you want to end up with sine only and get rid of the cosine here, what you can do is start with the Pythagorean identity. So sine of theta all squared plus the cosine of theta all squared equals 1. That's the Pythagorean identity. And what we want to do this time is get rid of cosine. So I'm going to make cosine the subject. Then I'm going to shove that into there, which is sine squared theta, take away 1, take away sine equals and we've got 2 lots of sine of theta all squared, take away 1. That is that, which comes from that, which uses that, if that makes sense. All right, let's go with complementary relationships or some further symmetry properties. Okay, this is tough to see. All right, but here we go. So this triangle here, girls, that one there, don't think this is controversial. That's exactly the same as this triangle, because I go theta up from 0. This starts at pi on 2, and I go theta across. Okay, or I go theta in that direction. It'll be the same thing. So these are the same triangles, and if they are the same, that A value is the same as that A value, and that B value is the same as that B value. Same over here. If we go or use pi on 2 as an anchor point and go forward, then we get these two same triangles with that A value being the same as that A value, that B value being the same as that B value. All right, this one here is a pretty nasty problem, and I've thought about this one a lot over the years and been asked this question a lot of times by students. All right, so what we've got here is tan of theta equals 0.6. Okay, that's what we're looking at there. That's the right angle triangle. And what we want to do is start at pi on 2 and go theta across. So I'm just going to redraw that triangle as best I can to scale, but it's not fantastic. So if that's the case, this distance here, that's just 1. This distance here is 0.6 because that's 0 all the way to 0.6. So that must be 0.6. All right, now what we're trying to do is find out the value of tan at this particular point, or at this particular point on the unit circle. Now, how are we going to do that? Well, what it will do is it's going to go down here and it's going to cut the tangent below -1 somewhere down here. So I basically need to work out, let's call this alpha over here. That's what I'm going to do. I'm going to work out alpha, and that'll tell me where it hits the tangent down here. Now, what most students do on this question here is they go opposite over adjacent on this, and note that this 0.6 is negative, okay, because that x value there is negative over there, and try to tell me that the tan of this is equal to negative 0.6, to which I would sort of go, so that's what you're saying it goes through. Okay, and I mean, my drawing is not fantastic, but I can clearly see that that line is not going to go through negative 0.6. It's much lower than that, or below -1 at least. So here's another way to visualize this. That's 1. That's theta. That's negative 0.6. Now I'm going to just draw or complete this rectangle. That with that, that with that. That's 1. That's negative 0.6. And this is alpha. Right, so how are we going to find the tan of alpha? What we're going to do is the opposite over the adjacent, or we're going to say that the tan of alpha is equal to -1 over 0.6, or 1 over -0.6, which is equal to -10 on 6, which is equal to -5 on 3. So that one is not -0.6, it's -5 on 3, or -1 2/3, which seems appropriate. Here's -1, it's saying it's roughly -1.6. So that seems appropriate. So watch out for this question here. It's a tricky one. All right, so on to these questions here. Okay, and again, exploring these complementary relationships, we can see that the anchor point for all of these questions is pi on 2 or 3 pi on 2, i.e. on the unit circle, we're starting here and here. So you can tell that all of these questions use or will test your understanding of, is this triangle, or can we recognize that this triangle is exactly the same as this triangle if that's theta and that's theta. All right, so first of all, it gives us a bit of information. Cosine of theta is 0.88. And it also tells us that the sine of alpha, so this is alpha, a completely different angle, is 0.1736. So the first thing we'll do is, because I can see I'm using sine, cosine, and tan, I'm going to need to find out these unknowns, sine, and tan over here. to use them later on. Okay, so to do these unknowns, what I'm going to do is use Pythagoras' theorem. I know that that's one. I'm just going to slam them both into Pythagoras' theorem, which is the longest side take away, or the longest side squared take away the square of the known shorter side. Is that 8829? Yep, all squared. So that value there is 0.4696. And this one over here, I'm just going to edit that, 0.1736. A lot bigger, it's 0.9848. All right, so there's our key values that we're going to use to answer these questions. And to do them, what I'm going to try and do is really emphasize the symmetry by actually going over to a unit circle diagram to show you this. So the first one is sine of pi on 2 plus theta. So I drew this prior to starting this particular question so that I could speed things up. So I'm just going to try and draw that as much as I can to scale. So that's 0.88 roughly there. The right angle is going to go up and across, and that would be theta. So 0.8829, and that one there is 0.4696, I think it is. All right, let's change color because, well, it's more fun. We're at pi on 2 and we're going theta more. That looks roughly like 30 degrees, so 10, 20, 30. So around about there. Let's redraw our triangle. So I hope it makes sense to you that these two triangles here are the same. Okay, it's the exact same triangle, which means this value here must be the same as this value here, and this value here must be the same as this value here. Now, what are we after? We're after the sine. So we're at this point here on the unit circle, and I will go across and note that this is the value that I'm after. It's positive, okay? And the value here is going to be this value here, which is the same as this value here, which is going to be 0.8829. So go back to your notes and pop that in, equals 0.8829. All right, and for this question here in your notes, what I would do is do a unit circle here and just try to draw that symmetry property so that you can see that that one and that one are the same. All right, let's do this one here. So we're at 3 pi on 2 take theta. So we want the cosine of 3 pi on 2 take theta. So we're over here, let's change color again. I don't know, like, what do you want to use this time? Green maybe? 110. Okay, so we're somewhere here. So we're like 3 pi on 2, and then we're going backwards theta units. Okay, so again, hopefully it's pretty obvious that these are the same. Okay, this time we're after the cosine. The cosine is this x value over here. That's what I'm interested in. Now this distance here will be the exact same distance as this one here. Okay, the only thing is the distance will be negative. It's going to hit the negative value of this. So that's going to be equal to negative 0.4696. Negative. Right, so go and pop that in your notes, negative 0.4696. And again, just try to draw that with a unit circle in your notes there to reflect that. All right, the last one, tan theta take pi. So tan theta on 2 take pi rather. So we're here, okay, and let's just check what that question was. Tan pi on 2 take theta. So we're starting at pi on 2 and we're going backwards theta. So we're going to end up somewhere over here. Again, let's just change color. All right, so there is theta. Okay, so what we need now is to work out where the tangent's going to hit. which is going to be up there somewhere. Let's extend this out. Somewhere up here. Now that is going to be 1, so I'm going to get a reasonably high tangent. All right, now that I know that, it gives me some inclination as to what the answer is going to be. Right, so let's do this. Now, what I'm actually trying to work out now is to work out this tangent here. I need to work out what this angle here is. I'm going to call that alpha. So to really do this, I'm going to redraw, like I did in that first question, redraw this. And I've got this distance here, which I know is 0.4696, and the height, which is 0.8829. That is theta. And then I'll just fill out the rectangle, that. And this is alpha. So what I'm going to work out is the tan of alpha. And what it's going to be is this is the opposite and this is the adjacent. So 0.8829 over 0.4696. It's positive, so none of those are going to be negative. So we'll just throw this into the calculator and see what it turns up. 0.8829 over 0.4696. 1 alpha equals 1.880, which seems reasonable, okay, somewhere up there. Now again, the most common mistake I see that students do with this one is they'll just go for theta and they'll go opposite over adjacent and get roughly a half for this. And again, you can see that it just can't hit the tangent at a half. It's just not going to do it, okay? So hopefully you got your wits about you with these ones here and sort of thinking about what your answer should roughly be. So that one was, did I write 1 point? No, 0. Oh no, it's 1 point. Yes, that's correct. So let's go and fill that in. Equals 1.880. Okay, and again, make sure you put a diagram in your notes there, girls, because that's something from year to year when I teach this. I have to really practice this part of the topic before I come into class, otherwise I stuff it up. Okay, so let's go with this. I'm going to pause the video at this point here to fill out the unit circle on the other page, and then I'll do these questions. Okay, so we're ready to go, and what I'm again going to do is try to emphasize the symmetry properties by doing a lot of this question on a 2-scale unit circle. So here is the triangle that is in your notes over here. I've just redrawn that so that I don't have to keep flicking around. I've also just popped in each of the questions here. Right, so let's draw this first of all in the first quadrant, so 0.98. Right, so it's like somewhere over here. Right, and what it's going to do is come up to roughly 1.7. This one is actually hard to draw to scale only because it's so small, and I've got this dodgy stylus that I bought about 7 years ago now that I'm using, old technology for an old man. All right, so there it is there. All right, now what I'm going to do is the first question. Let's change color. It's this one here, sine of 3 pi on 2 plus alpha. So here's 3 pi on 2, and alpha is about 11 or 12 degrees, it looks like, further on. So there's my triangle. Doesn't really look it, but we're going to say that these are the same. If I've gone alpha units up there and alpha units across there, then it's going to produce exactly the same triangle. That means that value there is the same as that, and that is the same as that. So we want the sine of 3 pi on 2 plus alpha. So we want this value here, which is going to be the same as this value here, albeit it's going to be negative, okay? So this one's positive, and it's 0.9848, but this goes below the x-axis, or in the negative direction of the y, so it's going to be the negative version of this. So this one is going to be negative 0.9848. So fill that in your notes, and again, try to articulate what you're doing with diagrams. Right, this next one, is going to be pi on 2. So we're starting there as our anchor point and we're moving back alpha. So moving back roughly 10 or 11 degrees. So here is my triangle. Okay, and what we're after is the sine value, which is this value here, which must be exactly the same distance as from there to there. So that just goes up to there. So whatever that was, that will be, and it's positive as well. So nothing to worry about even with positives and negatives there. That one was a bit easier. All right, and the last one is this one here, the dreaded tangent question. So we're doing 3 pi on 2, and we're going alpha units in the positive, okay, or in the anti-clockwise direction. So let's change color to be consistent. We want to use blue maybe. Yeah, let's go blue. Okay, so a bit dodgy, Mr. Miller, but it'll serve the purpose. Alpha. All right, so what we're saying here is that, well, I'm guessing the tangent is going to be big this time, okay? Because if you look down, all right, where is it going to hit the tangent? Okay, we're going to be going down here. It's going to hit it somewhere, like this is -1, and it's way below there, 6, 7 times the distance. So I'm expecting tangent to be big. Now that's important to know. Okay, now what we're going to do to get the tangent is actually find out what this angle here is. We're going to call this one theta. All right, so to do this question, I find it really helpful if I draw this in. So that's alpha, and that is going to be 0.17 whatever, okay, because that distance there is that distance there, which is that distance. The height will be 0.98 whatever it is, okay, and that's going to be negative, okay, because we're going down, okay. All right, now I'm just going to complete my rectangle. That's the same as that. That's the same as that. And we've called this one theta for the purpose of the exercise. So the tan of theta is going to equal the opposite over the adjacent, which is negative 0.9848 over 0.1736. Jump on the calc. That's still in there from before. Over, let's go to 4dp approximation, 0.1736. And as suspected, the tan was going to be low, negative 0.5673. Okay, that's our value, 5.6728. My bad. Negative 5.6728. All right, so hopefully you've grasped those questions there now a little better. All right, now the final question that we're looking at is the classic Pythagorean question. Okay, so they tell us that cosine x is 4/5, and we're in the fourth quadrant. So let's get an idea of that by sketching that up with a unit circle. And we're going to say that that's 0.8. So cosine x is that. Okay, so I'll try and roughly draw this to scale. Okay, so there it is. That's going to be 4/5. Okay, that's x, that's 1, and what they want us to find out is the sine. That is, they want us to get this value here. Okay. Right, so the way we're going to do that is with the Pythagorean identity. Okay, so I'm just going to state that again. So cosine theta all squared plus sine theta all squared equals 1. Right, let's slam in what we know. We know what the cosine is. It's 4/5. So we're going to do 4/5 all squared plus this one, which I don't know, equals 1. Now, that's the same as sine theta all squared equals 1 take away 16 on 25. So I evaluated the square. That's going to be 25 on 25. Take away 16 on 25, which equals 9 over 25. Now what we're going to do is root both sides. So the sine of, and I'm going to say the sine of x now, and I probably should be consistent with my naming, is equal to plus or minus 3 on 5. Now, which one is it going to be? So we're going to say, but we're going to say 3 pi on 2 less than x less than 2 pi. That's where we're looking. Therefore, sine x equals negative 3/5. So it's the negative version that I'm accepting, or I'm vetting out the positive one because of where I am in the unit circle. Okay, so that's sine of x. Now what we're going to get is the tan of x. And this harks back to what we need to remember from the start of the lesson, which is the identity for tan x is simply sine x over cosine x. Now we worked out what sine x was. That was negative 3/5. And we know what cosine is. That was given to us. That's 4/5. So that's going to be negative 3/5 divide 4/5, which is the same as negative 3 on 5 times 5 on 4. Those 5's cancel out, leaving us with negative 3 on 4 as the answer. So tan of x is equal to negative 3 on 4. Right, so there you have it, some further symmetry properties there and some pretty tough stuff there. So spend your time on that one. It's really well worth sort of really exploring that unit circle there and getting a good understanding of it.